AI agents are transforming how we approach automation and decision making. Recent headlines suggest that 2025 could be a breakthrough year for this technology, even with some predicting AI agents will replace traditional roles. While traditional software architecture relies on carefully orchestrated systems and predefined business logic, agent-based approaches offer a more dynamic and adaptive solution. What makes these systems truly powerful is their composability. You can combine different agent patterns like building blocks, routing agents directing tasks to specialized chains, or monitoring agents overseeing multiple processes simultaneously. Even more impressive is how these components can be cloned and scaled. Imagine taking a successful agent pattern and replicating it across different domains or tasks. A key resource for understanding this landscape is Anthropic's recent paper, Building Effective Agents. It provides practical guidance on when to use agents versus traditional approaches. Today we'll examine how to choose between these methods and structure your systems effectively. Let's dive in. Traditional workflows follow preset paths, while autonomous agents can create novel solutions, learn from experience, make independent decisions, and adapt to changing conditions. The best example I could think of to help describe a true AI agent would be to use one in an edge computing node. This could basically be a node that's on a robot in a manufacturing environment. You can think of it as the brain of the robot. It almost sounds like a consciousness because it could have full awareness of its documentation, its sensors, its history, its physical layout, and much more. And all of that could run on a Raspberry Pi or a similar computer. And of course, this data could be mirrored in a digital twin in the cloud and monitored by other more centralized resources. But as an edge node, you get the benefits of real-time processing capability, network independence, enhanced security, and immediate decision-making. This local processing power is essential for true autonomy, allowing machines to think and act independently without constant central oversight. Let's examine a practical example of an autonomous agent in action. Consider a robotic assembly system equipped with an edge computing node, comprehensive sensor array, access to historical data, and real-time monitoring capabilities. Let's see true autonomy in action when this robot encounters unusual vibrations. First, it analyzes the vibration patterns. Next, it searches historical maintenance records. It identifies similar past incidents. It might even need to use a web browser to find some information, or it might need to write its own code in order to do some special analysis. It determines the root cause, which in this case happens to be debris on the timing belt. It evaluates the operational capacity and initiates predictive maintenance. And the autonomous responses, creating maintenance tickets, ordering replacement parts, scheduling optimal maintenance windows, adjusting operations to minimize wear. Also, when we're talking about the human in the loop here, the agent may need to make some code changes and may need to seek some approval as well. Let's explore different workflow patterns and their industrial applications. Now, a lot of these workflows that I'm going to talk about are like agents. They can certainly contain agents, and there's quite a few agent frameworks out there like LangGraph, AutoGen, Pydantic AI, and Crew AI that you can utilize these patterns with. Prompt chaining decomposes a task into a sequence of steps, where each LLM call processes the output of the previous one. You can add programmatic checks on any intermediate steps to ensure the process is still on track. So here are some examples of when you would want to use prompt chaining. For one, when your task naturally breaks down into clear sequential steps. When each step's output needs to be verified before proceeding. When you need high reliability and traceability. When the process flow is well understood and consistent. And this is typically your go-to pattern for the most predictable results in most cases. In this manufacturing example, this creates a sequential quality control process. First, the vision system detects a paint defect. The analysis prompt determines the defect characteristics. The root cause analysis prompt evaluates contributing factors. The solution prompt generates correction parameters. The validation prompt confirms fix effectiveness. The routing workflow classifies an input and directs it to a specialized follow-up task. This workflow allows for separation of concerns and building more specialized prompts. Unlike prompt chaining, routing doesn't require sequential steps. Instead, it focuses on directing input to the right specialist. So when would you use the routing pattern? Well, when dealing with diverse types of inputs that require different handling. Also when you have specialized systems or teams for different scenarios. Also, when the classification of issues is clear and well-defined. For example, a machine sensor can clearly identify if the issue is a temperature-related issue, or a mechanical failure, or a quality defect. Or so basically when you need to direct different types of problems to specific experts or systems. In our manufacturing example, the system receives an equipment alert. It classifies the issue, the type or severity, it routes it to a specialized department, and generates handling protocols. The parallelization pattern can be broken down into two key variations. Sectioning, which is breaking a task into independent subtasks run in parallel. Or for voting, running the same task multiple times to get diverse outputs. While this might sound similar to Orchestrator workers, the key difference is that parallelization handles truly independent tasks or multiple instances of the same task, while Orchestrator worker involves coordinated, potentially interdependent tasks. So you would use parallelization when tasks can truly be performed independently, when you need redundancy for critical decisions, when processing time is crucial and tasks can be parallelized, when you want consensus from multiple systems for increased reliability. In our example paint application, parallel monitoring of viscosity, environment, and robot movement go on. Then multiple agents evaluate the paint quality, and we end up with a consensus-based quality approval. In the Orchestrator pattern, a central LLM dynamically breaks down tasks, delegates them to worker LLMs, and synthesizes their results. Unlike parallelization, the Orchestrator maintains active control and coordination over the workers, making real-time adjustments based on their progress and results. So you would use this Orchestrator pattern when tasks require complex coordination between multiple systems, when subtasks are interdependent and need central oversight, when the division of work needs to be dynamic rather than predetermined, when you need a single point of control for complex operations. Here we have an assembly line automation. First, the central orchestrator evaluates the overall process. It delegates specific tasks to specialized robots. It coordinates the timings and the resources. It synthesizes the progress reports. And finally, we have the Evaluator-optimizer pattern, where one LLM generates a response while another provides evaluation in a feedback loop. This pattern is unique because it focuses on continuous improvement rather than just task completion. This makes it ideal for optimization scenarios. So you would want to use this when you need continuous process improvement, also when the quality of solutions can vary significantly, when you have a clear evaluation criteria, as well as when iterative improvement is more important than immediate results. In our example, the production system runs a process, the evaluator monitors the metrics, and the optimizer suggests improvements, and we get a continuous feedback loop that maintains quality. While AI agents represent an exciting advancement in automation, it's crucial to remember that traditional workflows remain the backbone of reliable industrial processes. When we need predictable, consistent results, which is often the case in manufacturing, these tried and true workflows are usually our best choice. What's particularly powerful about these patterns is their composability. You can mix and match them to solve complex problems. For example, you might want to use routing to direct different types of issues to specialized prompt chains, or have an Evaluator-optimizer pattern monitor multiple parallel processes. The key is to understand each pattern's strengths and combine them thoughtfully. Think of workflows as our reliable foundation, while agents are powerful tools for specific scenarios where adaptability and complex problem solving are required. The key is knowing when to use each approach. For many applications, a well-designed workflow will be more efficient, easier to implement, and more cost-effective than a complex agent system. Remember, just because we can use an AI agent doesn't always mean we should. Start with the simplest solution that meets your needs, and only add complexity when it truly adds value. Often the best solution might be a combination of traditional workflows enhanced with agent-like capabilities where they make the most sense. Thanks for watching, and don't forget to subscribe for more practical content on AI and automation in industry.